Alright, you guys, I want to talk about similarity in right triangles, and in order to do this section you have to know how to simplify with radicals. So we've already learned how to simplify with radicals, and now the reason why we learn to simplify with radicals is because of this thing called the geometric mean. And first of all, I want you to underline where it says x is the geometric mean, and know that geometric mean always goes here and here in a proportion. So whenever it says find the geometric mean, like this does, we're going to immediately put it in these spots of the proportion. What goes in the other two spots? The two numbers they give to you. So here's my example, example 1. It says find the geometric mean of 3 and 12. So I set up a proportion and I immediately put x in the geometric mean because I don't know what it is. I'm trying to find it. And these are the two numbers I'm going to use, 3 and 12. So I'm going to set up a proportion, and now we're going to cross multiply to solve this. So x times x is x squared. It's equal to 3 times 12. So x squared is equal to 36. When you take the square root of both sides, the nice thing is 36 is a perfect square, and x is equal to 6, and we have just found the geometric mean. Okay, we're going to do the same thing again. Find the geometric mean between 32 and 2. Once again, I set up a proportion. I put my geometric mean in these two spots. They asked me to find it between 32 and 2. Cross multiply. X squared equals 32 times 2 is 64. Square root. Again, 64 is a perfect square. Square root of 64 is 8. And I'm done with the problem. The most unfortunate thing for you is that they're not always going to be perfect squares. So let me show you the next example. In this next example, we're asked to still continue to find the geometric mean between 6 and 20. So, once again, I put my geometric mean in these two spots. It's between 6 and 20. I'm going to cross multiply. X times x is x squared. 6 times 20 is 120. Take the square root of both sides to isolate your x. X is equal to square root of 120. This is not a perfect square, so you have to reduce it down. Now, in our perfect square charts, we have 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and 121. I'm going to stop because 120 is right here. It's not on my list. Now, where do I start? I start at half of this number. Half of 120 equals 60. And so I'm only going to check my perfect squares that are 60 or below. I want to see if these divide into 120. I need to see if they divide. So I take my calculator out and see if I get a perfect number or if I get a decimal number. So I grab my calculator. It's a guess and check system at this point, and I go 120 divided by 49. Nope, I get a decimal. 36 divides into 120. Let's find out. 120 divided by 36 is equal to 3.33. Repeating, no. 120 divided by 25, 4.8, no. 120 divided by 16, well, 120 divided by 16 is 7.5, no. 120 divided by 9, 13.3, no. 120 divided by 4, yeah, a nice number. So this breaks into the square root of 4 times the square root of 30. We chose the square root of 4 because it is a perfect square. My final answer is 2 square roots of 30. What's going to happen is you're going to get very good at looking at these numbers. Knowing your divisibility rules really help. I look at the number 9. There's no way I can get 9 to end in a 0 unless I multiply it by 10. That's not going to happen. How can I get the 6 to be multiplied to get a 0, I'd have to multiply it by 5. And if I do 36 times 5, I get 180. 5 could end into a 0, but for 25s, I know they have to either be like 25, 50, 75, 100, 125. That doesn't work. 16, 9, you can learn your divisibility rules to help you do this quickly. All right. Theorem 7.3. Let's talk about this. This is a right triangle. I'm going to label this triangle ABC. And here's what this theorem says. The altitude to the hypotenuse of a right triangle. Now, what is an altitude? An altitude measures the height. So you start at the top of the triangle and you go straight down, make 90-degree angles. I've created a new point. I'm going to call this point D. This line I drew straight down is my altitude. So the altitude is segment CD. Okay, so the line that goes straight down is your altitude. Now, according to this theorem, this altitude divides the triangle into 2 more triangles. And sure enough, I got this triangle ADC, this medium-sized one, and this little tiny triangle BDC. And this theorem is telling us that these 2 little triangles, I'm going to call this triangle 1 and triangle 2, are similar to the original triangle ABC. So I have 3 similar triangles. How do I know they're similar? I just want to show you that the easiest way to name the similar triangles, I think, is to match up your angles, and I need matching angles. And so in order to get my matching angles, I'm just going to create 2 numbers I know that adds up to 90. Now you're going to choose the numbers 30 and 60. And I'm going to make this little angle right here 30 degrees. I'm going to make angle B 60 degrees. And if this is 30 and angle D is 90, then this angle up here has to be 60, and this angle has to be 30. And the reason why I did that is because when I want to name my similar triangles, I can now say that triangle ABC is similar to, now we're going to do triangle 1. In order to match it up, I'm going to match up my angles. I said angle A is 30, angle B is 60, and angle C is my right angle, it's 90. So when I match up my next triangle, triangle 1, I am going to match it up, this is going to be triangle 1 by the way, to the same rule of 30, 60, 90. So I'm looking at triangle 1 and I say, okay, in triangle 1, which one is 30 degrees? Well, it's angle A, which one is 60 degrees? Angle C, and which one is 90 degrees? Angle D. This is going to be similar to triangle number 2. And I'm also going to do the same order of 30, 60, 90. So in triangle 2, my 30-degree angle is angle C, my 60-degree angle is angle B, and my 90-degree angle is still angle D. So these are the 3 similar triangles I get according to this theorem, 7.3. Now, because I have similar triangles, I know by our definition of similarity that I can set up proportional sides. And I don't want to have to draw 3 triangles every single time to set up proportional sides. And so we have a corollary to help us do this. It's a shortcut. It's a cheating method. But the corollary is sometimes difficult to understand, and so I have renamed the corollary the spider. And it's going to seem confusing at first until you see some examples, but please bear with me. We're going to talk about the spider. So I'm going to draw my right triangle, and here's what it says. The length of the altitude to the hypotenuse. Now don't forget, the hypotenuse is right here. This is my hypotenuse. So I'm going to draw the altitude down to this hypotenuse, and I get this new shape. Now, according to this, they're saying the altitude, I'm going to call this altitude A. They're saying this altitude is the geometric mean. So I'm getting this geometric mean word again. The altitude is a geometric mean, so I'm going to put it right here and right here. And we need 2 numbers that it's a geometric mean between. Well, they tell me the 2 numbers are the lengths of the segments of the hypotenuse. Notice my hypotenuse got cut into 2 pieces. It got cut into this piece right here that stops. I'm going to call this piece B. And it got cut into this piece right here, this little tiny piece. I'm going to call this piece C. So according to our rule, this gets divided into piece B and piece C. So how is this related to a spider? Now you guys have to use your imagination, all right? When I think about spiders, I'm going to say spiders are inside the house. Spiders are inside the house. So the house in our case is the triangle. This right here is our house, and this is my spider in the house. So please circle your spider. And anytime you have a circle, it's going to be the geometric mean. So the spider is the geometric mean. Now, what's it the geometric mean of? I'm going to show you where the spider is standing. Remember, we have little spider legs that come out of the spider. So here's one spider leg standing on the B, and here's one spider leg standing on the C. So imagine this is like some creepy spider, and here's his legs, and the spider is a geometric mean between where he's standing. So I'm going to rewrite this as the spider is the geometric mean between where he is standing. The spider is a geometric mean between where he is standing. So he's standing on the B and the C. So the spider A, the spider bodies in the circle, is a geometric mean between where he's standing. He's standing on the B and the C. Okay, now I know it seems confusing until you see an example. I got to show you one more example. And this is corollary number 2, and I named this corollary the peen boy. So let me talk about the peen boy. If I offend you guys, I'm sorry, but this to me is an easy way to remember it. Alright, so we have in our picture our right triangle. This length is the hypotenuse, and we have an altitude being drawn to the hypotenuse. And similar to my other problem, this was A, I labeled this B, and I labeled this part C. Okay, now I want to say that this whole length from here to here is the hypotenuse of the right triangle. So I'm going to call this H for hypotenuse. H is equal to hypotenuse. And I have two legs of this triangle. I used A, B, and C, so I'm going to call this leg D. I'm going to call this leg E. Now when you read this statement, it's challenging to read and understand. It says the altitude to the hypotenuse of a right triangle, it separates the hypotenuse so that the length of each leg of the triangle, and the legs are D and E, is the geometric mean, so I have the geometric mean again, of the length of the adjacent means next to, hypotenuse segment, and the length of the entire hypotenuse itself. Well, I'm going to say that there's an easier way to remember this, in my opinion, and I call it the peen boy. And to help you understand this, I want you to remember that when you have boys, you want to send them outside to play. So the boys are outside of the house. So this is my house, and I'm going to go ahead and I'm going to circle a boy. So this is one of the boys outside of the house. And very much like the spider, the boy is also standing. So where is the boy standing? The boy is standing on the B. Now this boy has to go pee. And boys, just like girls, they never want to pee where they stand. So this boy is going to pee off of where he stands. He's standing on this red line, so he's going to, now bear with me, he's going to, here he is, he's peeing. Now where is he peeing? He's peeing right here on this H. And so what I'm going to tell you is that the boy is the geometric mean between where he is standing and where he is peeing. The boy is a geometric mean between where he's standing and where he's peeing. So when I set up a proportion I know the boy, in this case it's D, and I'm going to circle him because he's the geometric mean between where he's standing. This boy is standing on B, and where is he peeing? He's peeing on the H. The thing is, I've got another boy. Who's my other boy? Boy E. He's also a boy. So I'm going to put him right here. He's also a geometric mean. Where's this boy standing? This boy is standing on the C, so he goes here. Where's this boy going to pee? He's not going to pee where he stands. He's going to pee right here, also on the H. So here's how I make proportions using right triangles. And I know that the boy is the geometric mean between where he's standing and where he's peeing. This is going to help us remember how to set up our proportions. Alright, let me give you an example of what I'm talking about. Don't forget, spiders are inside the house, the boys are outside the house. Spiders are in the house, boys are outside the house. So here's my example. And they want to know what is the value of x and what is the value of y. I'm going to suggest to you that you try to always start with the spiders if you can. Start with the spiders. So in this problem, I see a spider and a boy. Right? This 6, he's a spider. Why? He's inside the house. Where is the spider standing? He's standing on the 2 and he's standing on the x. So we're going to set up our first proportion. And what do I know? I know the spider is a geometric mean, so he goes here, between where he's standing. He's standing on the 2 and he's standing on the x. I'm going to solve this proportion. So I'm going to cross multiply. 2x is equal to 6 times 6 is 36. This is not a square root problem. I don't have x squared. I have a normal proportion. So I'm going to divide by 2. And I get x is equal to 18. There's one answer. I have to plug this in. Back into the problem. We're going to plug it in. So where this x is, this is now 18. Okay, second part of this problem. I got a boy outside. The boy is outside. Here's my boy right here. Where's this boy standing? He's standing right here on the x, which is now the 18. The boy has to pee. Where is he going to pee? He's going to pee off. Now, I don't have a line right there. This line is the hypotenuse. How long is it? It has a length of that 2 plus that 18, a total length of 20. And this is going to allow me to set up my second proportion to find y. What do I know? The boy is a geometric mean, so he goes here, between where he's standing, which is 18, and where he's peeing, which is 20. I have to cross multiply this problem. Y times y squared equals 18 times 20 is 360. This is a square root problem. Unfortunately, 360 is not a perfect square. You have to break it down into the perfect squares. The nice thing about this problem, I see a 36 immediately. So 36 times 10, and 36 is my perfect square. So I get 6 square roots of 10. And I have my value of y. Okay, let's do 2 more examples and I will be done. Clear my ink. We're going to solve for x right away. I notice x is a spider because he's inside the house. Here's my spider. Where is he standing? He's standing on the 15 and he's standing on the 5. I'm going to set up my proportion. The spider is a geometric mean, so he goes here between where he's standing. We're going to cross multiply. X squared equals 75. It is a squaring problem, so I have to take the square root. 75 is not a perfect square. What perfect square factor divides evenly into it? 25. The 25 times 3. Final answer, 5 square roots of 3. Okay, very last problem, solve for x and y. Before I do this, I got a problem. I got a boy. This boy, 15, he's standing on the x, but he's peeing off. I don't know how long this is. I don't know how long the x is, and I don't know how long the hypotenuse is. We have to use Pythagorean theorem to find the length of the hypotenuse. So we're going to use Pythagorean theorem. So I have a squared plus b squared equals c squared. The c is the hypotenuse, so let's just call that c. I have 15 squared plus 20 squared equals c squared. Using my calculator, 15 squared, 225 plus 400 equals c squared. 625 equals c squared. Square root. Man, 625 is a perfect square. C is 25. So this length is 25. This is going to help me do my problems because I have two boys, and here's my problem. This boy is standing on the x and he's peeing on the 25. Okay, so the boy 15 is a geometric mean between where he's standing and where he is peeing. I'm going to set up the other one as well. I have another boy here. This boy is a geometric mean, so he goes here between where he's standing, which is the y, and where he's peeing, which is also the 25. So once again, you have to cross multiply and solve these, and when you cross multiply and solve, you get this. 25x equals 225 divided by 25. X equals 225 divided by 25 is 9. And for my y, 25y is equal to 400 divided by 25. Y is equal to 400 divided by 25 is 16. Now this is a very long assignment, long notes. I apologize for this. We have 2 days we're going to work on this, part A and part B. And so we're going to spend a day in class working on this as well so that you guys can get help setting up these proportions. Alright, you guys, you have a great day. I will see you in class.